Good morning, everybody. Hope you're doing well. Let's see. Yeah, it looks like people are still waking up and coming in. So, okay, let's talk a little bit about what's going on here. Let's review some ideas. Let's see. I can't think of anything off the top of my head. Everything's been turned in. I think we're, on the right track in terms of how we're operating the course, where to turn things in again, how to do that scanning and everything. So by now we've had a lot of practice, so we're starting to get things going. So anyway, that's good to know. What else do I want to do here? Let's go to the iPad here. And let's recall a few ideas that we were talking about yesterday. Okay. Um, so yesterday we started talking about numerical approximations. Now this comes from a Riemann sum. So if you all remember that definition here, and yes, this goes to infinity, right? So this is kind of some questions here. What we're focusing though here, this is the definition. This is equal. This is exact. So I want people to know that when we take this particular sum here, right, we take that limit as n goes to infinity now. This is exact. It's equal. But we are approximating the area under the curve, and this is where we're at here. We're going to look at an approximation. So this is all without the limit. Because remember, we're partitioning our interval of equal length, delta x, right? This is the partition. Oops. Of equal length, delta x, and partition that interval a, b. And now here we choose the number of partitions. We choose n. So we can have n as 5. We can have n as 10. We can have n as 100. Notice here, n is getting bigger. N is 1,000 now, right? So n is getting bigger. And eventually, if we say, okay, let n approach infinity, that means there's a arbitrarily large number of partitions. Well, this is exact. This area here, or this integral is exact. But we're not dealing with exactness in this topic. We're looking at the number of partitions being finite, not infinite. And so that gives us an approximation here. So this is kind of where we're at. And the key here is, I should say, using this formula here. Delta x, we're finding the increments here. And we need to know the length of the interval, that's b minus a, how long this particular interval is, okay? And given the number of partitions down here, and we divide by that, that gives us the increment, okay, of delta x. So that's kind of where we're at. And yesterday we looked at, if we looked at this in more detail, the concept of a left interval and a right interval. I'm sorry, left endpoint, right endpoint for particular intervals. Okay? So let me try to draw a straight line here. It'll be helpful for us this morning. So here's our straight line. And we say, okay, we have an interval from A to B. And we partition this. And what we've seen yesterday with these partitions is I can take, for example, an arbitrary interval. And I'm going to erase some of these. Oops, didn't want to do that. Maybe I won't erase it. Okay. I'm going to take an arbitrary interval, xi minus 1, xi, and then notice the key here was to identify the left and the right. And that was from yesterday. So here's an arbitrary interval. And we were using these endpoints to get the left endpoint rule and the right endpoint rule. So you can look at the notes. You can also look at the video. But what I want to talk about today is the midpoint. So if this is x0, this is x1 and x2. and so on. This will be xn. We have xn minus 1. The question is, how do we get, and if I do it this way, xi minus 1 and xi, how do we find these midpoints? So the midpoint for every interval. Okay, so that's what we're going to focus on. We're going to look at the midpoints now. And as you guys seen, we're approximating this area, but let's think about a midpoint of an interval. And look right in here, right? We need to get this value. And we need to do that for every one of our intervals. We need a midpoint value. Okay, so the question is, what are all these values here? How do we find them in general? Well, if you guys don't know, to get a midpoint value, let me just change these quickly. All right, here's xn. To get a midpoint value, a value that is midway between any two numbers in general, how you find anything that's midway is that you add the values and you divide by 2. Okay, it's also known as the mean of the two values, or the average of the two values. And so my notation that I gave people here in our notes is I said, okay, this will be M1, and this is M2, and this will be MI, and this is MN here, if we use our notation here, these indices. So you actually going to do things like add them, divide by 2, and that'll give you what we call the midpoint between any two numbers, but in this case, the midpoint of an interval. So for this particular interval here, the one you're looking at right in here, well, you can say, okay, Mr. Judge, I'm going to do this. I'm going to take the left point plus the right point, add them, divide by 2. And we do this for all I. And so you guys know I goes from 1 to n here. Okay, there you guys go. This is how we find the midpoint. And this is how we start our lecture. So let's kind of go back here to our document here. Numerical approximation. And this is the stuff we looked at yesterday. And so if we look at the midpoint here, those are right endpoints. Here's our midpoint approximation. And so everything that we see up here in our notes, midpoint approximations, I just talked about, meaning we're looking for these values again. Let's see, here we go. Well, color's red, I don't know. Maybe we'll use a gray. Finding those midpoint values of an interval. And what that looks like on a curve, again, all these down here, is you're going to see for every one of these midpoint values in our intervals, right, the corresponding points are up here. This is going to be the height of our rectangle. So we have our heights here of our rectangles for the midpoints. And that's what we're going to use, and it's going to be called the midpoint rule. So I derived for you all, and this is everything that we're talking about. And yeah, I think I want to remark too that books use this notation with the X with that line on top, because that's actually, the notation for the average. I actually say, let's go back and say average or mean. And it's also thought of as the mean or the average of the two values. So this is where this comes from. It comes from the idea that, the notation of X bar is actually a mean. And it's the mean of two numbers. This is why you say you add them and you divide by 2, right? This is how we have Al saying add the values, divide by 2. And that's absolutely correct. And that's also the mean of two values. So what I did for everybody again this morning, are in our notes, we looked at what's called the midpoint rule. And all the mathematics is actually here, meaning we're going to take the sum here, right, for the midpoint rule. We take the sum from I is 1 to n of f of mi delta x. So this is where we're at in our notes. Algebraically speaking, right, so we're right here. If you're adding, right, we're adding. Here's the sum. So we know this part. And then we factor out the delta x. And that's really what we're doing here. So we're going to use this information today. And this is called our midpoint rule. Okay, so I want to let you guys know. And the example it looks like we were working with, let's see if I can find that one here. Let's go back. I don't know why that shut down. It shouldn't. If we go back and look at the example we were working with. Okay, it's right here. We're looking at the left endpoint, the right endpoint yesterday. And let me write this down again so we can look at this in detail. We'll say recall, right? We're integrating from 1 to 2, e to the minus x dx. Okay, and now we're going to use, again, we're going to use n is 5 like we started with, and we want to determine m5. We want to approximate the integral using this particular approach, meaning not the left endpoint, not the right endpoint, using the midpoint. Now that's going to be f of x bar 1 plus f of x bar 2, right? Plus f of x bar 3, plus f of x bar 4, and of course we always run out of space, and f of x bar 5 here. This is in our bracket, delta x. All right, now a little bit of OCD. I want to fit this here for us together. All right. Well, a little bit better. Anyway. So remember, we got to look at the interval. And the interval starts at 1 and it ends at 2. So let's think of it this way here. When we start at 1, 1, 2, 3, 4, 5. Now let's go back over here. I think we should have it somewhere. Yeah, it doesn't matter. Let's just do the best we can here, okay? So this is really where all your work's going to be, ladies and gentlemen. Right, you already know delta x. In this case, delta x is going to be 2 minus 1 over 5, and we know that delta x is really 1/5. And 1/5 is actually 0.2. So here's 1. The next position is going to be 1.2. Just add that 0.2. And I'm going to do this a little bit bigger today. 1.2. 1.4. Keep adding the length delta x. 1.8. And finally, we end with 2.0. Okay, so we already have this information, and you guys know we have to find these midpoint values. We're going to use these values here. All right, so I'm going to erase this here. And again, you say to yourself, well, how do we get this particular value? Well, you take 1 plus 1.2 divided by 2. Okay, and so that gives you 2.2 divided by 2, which is 1.1. So that first midpoint is a 1.1 value. This number goes right in here. Okay, that's your x1, or I should say x bar 1, the first midpoint value. And then you could do a couple of things. You can say, well, am I going to repeat the process now for the next two values here? Because we did it with these two. And now can we do it with the next two? And the answer is yes. You can say 1.2 plus 1.4 divided by 2. And you know that's going to be 2.6 divided by 2, which is really 1.3. So we can put a 1.3 up here. That's M2. That goes up here. Now you may notice something here. Since delta x is 0.2, and if the distance between every endpoint is 0.2, then the difference between every midpoint is also 0.2. So you don't necessarily have to keep doing the arithmetic. If you know the value of that increment, delta x being 0.2, we can say 1.5, 1.7, and 1.9. So this makes this very, very quick. 1.5, 1.7, and 1.9. Okay, you guys okay with that? So I like to always say to people, guess what? The key is working with this computation, right? You're doing delta x is b minus a over n. And this really, combined with our formula here, is how we can numerically approximate. Partition into n subintervals, a finite number of subintervals of a small increment called delta x. So let's kind of finish this question here. So we do have to recall the function we were using. I want to use the same function as last time. And the function we're using is actually e to the minus x. So since it's e to the minus x, here's what this really looks like altogether, right? You should say m5 becomes e to the minus, well, what are the values of x? 1.1 plus e to the minus, what's the next value? 1.3 plus e to the minus, I know the increment is 0.2. I'm going to use that. Plus e to the minus 1.7 plus e to the minus 1.9. I'm going to multiply that by my delta x of 0.2. So ladies and gentlemen, this is where my arithmetic comes in. And there's a couple of ways we can do this here. Right? There's a couple of ways. I'm going to show you two ways to do it. So let's go to Microsoft Excel. And I noticed this morning when I looked over some of these notes and things, right? I noticed I actually didn't save the work we did yesterday. So the work we did yesterday was right in here, right? We looked at the left endpoint values. We looked at the right endpoint values and we approximated. We got a sum for each. Today we're looking at the midpoint values, and this is for M5. So I'm going to plug in here all these values here. So let me actually try to do something here. It's a little bit difficult for me, but anyway, what else is new? Juggling all these things. Minus. Okay, let's plug in those values. Autofill. And remember, we're going to add these because we need the sum. So this is what we get for the sum. And since I'm on the topic, let me do this one here again. So we have x, just to compare and contrast, right? And see how this works. Add these values. Okay. So they're a little different. exp raised to the minus, oops, say okay. Let's get rid of that little piece. Okay, so they're a little different. And you add these values. So we're kind of up to date now, right? But the point is, we were looking for this example, the midpoint, we're going to look for this value. And that's going to be 1.160785 times 0.2. So if we go back and we say, let's look for our screen here. All right, let's go back to the iPad. What you guys know is I have to take that number and then I have to multiply it with 0.2 right here. And that's going to give us our M5, what this is approximately. So midpoint rule, we're now going to use a TI. And we say, well, where's the TI? It's right here. Apologize for that. Okay. So TI is on 1.160,785 times that 0.2. And so we get approximately 0.232157. I'm trying to remember yesterday, what did we approximate these to yesterday? If I look at my notes here for the left endpoint and the right endpoint values, yeah, I don't think we had a given particular place. Okay. Anyway, let's double check here. I want you guys to see if you can see if you guys are awake. What did you get for Al5? And what did you get for, I am looking at it right now. What did you get for Al5? What did you get for R5 yesterday? Al5, I got 0.2565732. Well, see if you guys can get those out for me, your Al5 and your R5, okay, because this is M5. And this is what we have here for M5. And then I think what we did is we did do the exact value somewhere. If we check our notes for the exact value. This is R5, by the way. This was in Excel. And we got a TI version. Here's going to be, when we integrate it. This is the exact value. So if we go out to the nearest tens, hundred thousands, if it's even 10,000s, right? The exact answer is 0.2325. It's, I should say not exact again. It's a better approximation if we were to integrate this. 0.2325. So we know this is 0.2325 here. Okay, 0.2325. So if we compare this, we get 0.2322. Okay, so this is the value that we care about, and it's pretty close, as you guys can see. This is close. This is, I'm not going to say exact. I will use exact. I apologize. I know I'm contradicting myself, but it's a better approximation we get through actually integration. Okay, because we approximated this answer too. So M5 to this particular place value is 0.2322, right? Al5 to the same place value, we want to compare. Last one is R5. Okay, Excel, 1, 2, 3, 4, right? Oh, so this is 2101. 2101 for R5. Let's find the Al5. That's exact. Al5 with Excel 1, 2, 3, 4. So this is 0.2566. Now, here's my point to you, that what you have seen here is that this procedure, finding the midpoints or using midpoints or the average values in the interval, is actually a better approximation. Okay, it's a better approximation. It is closer to the quote-unquote integration value approximated. Okay, so you have a better approximation using M5 here. And that's my point to you guys. All right, I think I wanted to show people as well, if you go back to this question here, how you can do this in the TI, because sometimes people like to see that too. So let's go back to the TI and try to enter all of this here again, okay? So if you said, can I just put this all in my TI? You can, but you have to find the exponential key here. Second, E, remember, use the minus sign, okay, not subtraction. And the first point was 1.1. So come out of that, add, second, E to the negative 1.3. Come out of that, add, second, E to the negative 1.5. Come out of that, add, second, E to the negative 1.7. Move out of that, add, second, E to the negative 1.9. Come out of that, close this parentheses, and don't forget, multiply by 0.2. So if you find an error, please let me know. This is how you can enter it all in your calculator. And notice what the TI does. The TI does give you that example. So the TI gives us 0.321. Actually, the TI gives us a slightly different version, right? Well, it's the same up to a particular place value. I can point to it. Oh, you can't see my pointer. It's about 0.232 2, I guess, right? So it's 0.322, and if we approximate to the tenths, 100,000, 10,000ths, just like we did with the Microsoft Excel, this is the same value. So the TI does give us 0.2322. I'm going to write this down. Okay, so let's go to the iPad. I just wanted to show you how you can use a TI or some of your calculators. So this is for TI and for Excel. So you guys have that there, TI and Excel. Same value. All right. Okay, good. So I want to point out to you that this technique is even better than the left endpoint and the right endpoint. And I think it's pretty close to the 0.2325, which is what we're looking for. Okay, now that I reviewed and tried the midpoint rule, here's what we came here today for. This is what we paid for. This is actually the name, in my mind, this is the name of the section we'll be looking at. The essence of this section is actually to use what's called Simpson's rule. Okay, so Simpson's rule is what we really paid our fees for this section. Now, even if you look in your book regarding Simpson's rule, it's there. We prove Simpson's rule in your book. And since now that you guys are somewhat familiar with numerical techniques, since you see the left endpoint, the right endpoint, the midpoint formulas, let's go back and look at our notes here. And this is what we have. This is what I wrote for you guys. And I want you to take a look. Here's where we're at now. For Simpson's rule, you're still doing the same exact partitioning of your interval. Nothing's changed. It's the same technique. Okay? So Simpson's rule, and see if I wrote this down for us. Yes, here we go. Here's our formula. Here's what we're going to use today. And I didn't prove it here for you guys. Maybe I will do that later. Here's your formula. It's the same formula that's in your book. However, I want to remark about certain things here. N has to be even. And I believe n has to be greater than 2, really. But anyway, here's the formula. You still have delta x, but you divide by 3. Now, you could put that at the end, but we write it in the front for Simpson's rule. And I want you to pay particular attention to a few things. We start, and let me change this here. We start at x naught. Get rid of that. The next value is x1 and x2. This is the partition, right? We go to xn. But that's not what I want you guys to pay attention to. Okay? This is still functional evaluation. You're still adding. What I want you to pay attention to is what we call the weights. And I'm going to color this. Maybe that'll be a good color. Look at the weights here. We got 4, we got 2, we got 4, and this cycle continues 2, and it ends at 4. These are known as weights. And you might say to me, well, what weight did we start with? Well, we can call that 1, and we ended with 1. So even the starting point has a weight, 1, and the ending point has a weight of 1. So we can think of this as a sequence. And here's the sequence down here. So here's the point. Okay. Well, that's kind of weird. Yeah, we want to do this. Here's what we're doing. Well, it doesn't let me highlight. Oh, it's kind of locked in. All right, we locked ourselves out. I don't know how we did that. Let's try to do something. Okay. All right, well, maybe we'll come back in. No, we're still locked. Well, here's our sequence. It's 1, 4, if I can get this here. It's 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. So, yeah, well, okay, now we're free. Good. All right. But we don't get what we're looking for now. Okay, we're kind of locked out again. Doesn't matter. Let's go to the iPad and let's use Simpson's rule. So Sn, and I'm going to put it all the way over here. Starts with delta x over 3. F of x naught. Now remember the sequence. One, 4, 2, 4, 2, and so on. So here's your sequence. 1, 4, 2, 4, 2, 4, and 1. So this is going to be 4 f of x1 plus 2 f of x2 all the way down to 4 f of xn minus 1 prior, plus f of xn. Here's your formula for Simpson's rule. Okay, and so remember, you start with the partition. All the way back here, here's our partition. And let's get rid of some of these because we don't need them, right? This is not the midpoint rule. So here's the values that we need to use now. That's the x naught. This is x1, x2, x3, x4, x5. Delta x is still that 0.2. So when you use Simpson's rule, you're using every one of the values here. Okay? Now, you might say, Mr. Judge, you have a problem here. Let's see if you guys were awake. I can't use n as 5 here. Right? What do we have to use here? And let's try n as 6. Okay, so I want to remark here for you guys, this must be even. So I actually can't use the values. So you guys didn't catch that. I can't use the values in the prior problem. That's okay. Okay? And in fact, in this case, let's see what we're going to have to use here. We have delta x is going to be, again, the length of the interval divided by the sample size, since n has to be even when we're working with Simpson's rule. N has to be 6. Here's 6, and then the length of the interval here, again, is going to be, this is 2 and 1, so my delta x is going to be, so you guys know, 1/6. Okay? This is what we're going to use for Simpson's rule. It's 1/6. And so we replace this value up here by 1/6. But then the question becomes, since we have to partition, right? What does this partition really look like? Well, it's very, very simple, ladies and gentlemen. Remember, what do we start with again here? The first value is 1. Here's where we start. This is our x0. The next value, well, we have to add the increment. That's going to give us x1. So I have to take 1 and I add a 1/6. 1 plus 1/6, ladies and gentlemen, is 6/6 plus 1/6, and this is 7/6 here. Okay, we can do this. And so to get the other values, continue to add the increment. This will now be 8/6, 9/6, 10/6, 11/6, and notice 12/6, that is 2. So we're getting every one of those important values that we need to use Simpson's rule. But remember, Simpson's rule requires an even number of partitions. We couldn't use 5, so we got a problem. We can't compare. I mean, we can compare, but you guys know it's not 5. It's compared to 6. But this is the key, like I've been saying here. Okay? What you do for every question is what I'm showing you. Start with the number of partitions, find your delta x, and go partition your interval. Because now we get to plug in all these values in the formula here. Now you can say, do I plug in 1? Yes. Do I plug in 7/6, 8/6? And then we have to end with it. We do. So let's look at our particular case here. We'll write it out again, very clear. S6, delta x over 3 times f of x0. Remember the weights for f of x1 plus 2 for f of x2 plus 4 again f of x3 plus 2 f of x4 and then plus 4 f of x5 and finally f of x6, ladies and gentlemen. Okay? This is Simpson's rule. This is the formula you guys want to use. All right. Just plug in values now. Have some fun, right? What was delta x again? Do you guys remember delta x? Wasn't that 1/6? X0 is 1. 1.2. Oops. 7/6. 8/6. 9/6. 10/6. 11/6. You can say 12/6. I'm going to say 2. So this work now, to me, is 1 over 18. You say, how did you get 1 over 18? Go back here. 1/6 divided by 3 is 1 over 18. F of 1 plus 4 f of 7/6 plus 2 f of 8/6 plus 4 f of 9/6 plus 2 f of 10/6 plus 4 f of 11/6, and finally end that with f of 2 here. Okay? And don't forget what the function is. The function's e to the minus x here. Let's go back somewhere. Where's our function? There we go. Here's the function. E to the minus x. So plug in those values here, and you get s of 6 going to be, or s sub 6, e to the minus 1 plus 4 e to the minus 7/6. Got to remember how to write a 6. Plus 2 e to the minus 8/6 plus 4 e to the minus 9/6 plus 2 e to the minus 10/6 plus 4 e to the minus 11/6 plus e to the minus 2. So here's what you guys use for Simpson's rule. This is the formula. And we're now ready to enter this somewhere. We could do two things. We could do it in the TI. We can do it in our Microsoft Excel. I'm going to choose the TI this morning here, okay? So let's look at the TI here and see what you guys can do even with your calculators, right? And let's be careful here, right? Let's be careful here. I'm going to start. We're going to say what? Here, I'm going to put some parentheses. I'm going to say 1 divided by 18 here. Be very careful. Times, now let's open our parentheses here. Second e to the minus 1. Let's see if you guys can catch me with a mistake this morning, okay? Since you guys are really good with that, let's see if you guys can catch me on that. That didn't really fit. All right, that didn't really fit, right? Let's see if you guys can catch me. All right, plus, what's the sequence for Simpson's rule? There's 4. Now, some of you guys have calculators that require you to put times, so I'm going to put it times. I don't think TIs do, but I'm going to put that times anyway. Second e to the minus, what's our power now? Ooh, I think I better be careful. I have to put 7 divided by 6. Yeah, this is good. I like that with the TI because it kept us in the power position, and now we get out of there. Plus, what's the weight? 2 times second e to the minus. Now the power is going to be 8/6. Get out of that position. Plus 4 times second e to the minus. The next is 9/6. Good. Get out of the power position. Right. Plus, what's the next sequence value? The next weight is 2. Second e to the minus. This is now going to be 10/6. Get out of the power position. Plus, and notice I didn't put 2 times. But for TI, it's okay. I believe. Let's double check. Maybe it's not. 4 times second e to the minus 11 divided by 6. Get out of the power position. Now, remember, for the last value, there's no weight. The sequence is 1, 4, 2, 4, 2, and it ends with 4, and then followed by a 1. So this would be second e to the minus 2. We made a mistake. Let's go back. Right? We have to put, let's put plus. See what happens when you talk too much. E to the minus. Sorry. 2. Let's get out of there. Close the parentheses. All right, let's double check. I think this should work, even though we missed that one times and one of the multiplications. Let's hit enter. And notice what you guys get for Simpson's rule. S6 is approximately to the nearest 10, 100,000, 10 thousandths, 0.2325. Okay, so let's go back to the iPad. This is Simpson's rule, ladies and gentlemen. And yes, we did 6 approximate, or I should say 6 subintervals. We partitioned the interval into six subintervals as opposed to 5. What if I go back here and let's compare? 0.2325. Remember this? Let's go back and compare here. S6, 0.2325. And like I've been promising you guys, this particular approximation of all the others, right? You say, what are the others? Well, look at M5, 0.2322. Look at L5, 0.2566. Look at R5, 0.2101. And Simpson's rule gives us a value that is closest to the integration approximation, 0.2325. So Simpson's rule, to let you guys know, is a vast improvement over really the fun where you really start is left endpoint, right endpoint. Midpoint is a pretty good approximation. But Simpson's rule is the best. And so this is worth your fees here for this topic here. Okay, so in my mind, whenever you say to me, oh, guess what? You got to cover what's called numerical approximations. I always say to you, oh, Simpson's rule in a calculus test or in a calculus class, right? Simpson's rule. And that's the essence of it, because it's a more powerful formula, I should say, or rule that gives you an approximate answer much faster, much quicker. So what we say in math language is that this approach here, this formula converges faster to the exact value. You require less partitions for greater accuracy. Now, that doesn't mean you can't compute maybe S22. You can. It just means you have to use that formula that I gave you, and then you're going to probably have 22 things to sum, each with the weights. And remember, for Simpson's rule, you have weights. 1, 4, 2, 4, 2, blah, 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 end at 4. The last one is 1. That's the sequence of your weights in Simpson's rule. But you're going to use that, and you can actually compute S22. And ladies and gentlemen, that's going to be an even better approximation to the answer. Okay? And much faster. But there's other techniques. There's other numerical techniques. Really, there's a trapezoid rule. There's even more techniques that you study in more advanced courses in numerical integration. And you could even get a PhD in, numerical approximations, because you have numerical approximations for a lot of things. Not everything is nice in this world, as you guys already know. Not everything works like it's supposed to. Most of the time, there's things that you're going to have to go out and maybe possibly do numerical approximations. Maybe you have to find 648, right? Now, you're not going to use a TI to do that. You're not going to use Microsoft Excel to do that. You'd program a computer to do this. And so this is how this really works, ladies and gentlemen. So you want to get some use of background in numerical techniques, because even when you take some of your programming courses, they require you to know some numerical techniques. But to really summarize what you guys really have to do for every one of these questions is, here's the summary. First, most important thing is determine the number of partitions. They're going to give that to you. And then you have to find the increment, the length of the interval over the number of partitions. And then you partition the interval. You do that for every single problem. You follow these 3 steps. So you can say, okay, is this one? Yes, the first thing you do. So if you want to put this in steps, step 1, step 2, step 3. You do them in those particular steps, okay? And then you could do any numerical problem that they give you. But remember, for Simpson's rule, you have to have an even number of partitions. For the others, doesn't matter, okay? And you're not going to use 2 partitions for a Simpson's rule. Use something bigger than 2. And when I look at the book again, I'm looking at homework, and I already assigned homework to you guys. And I'm going to adjust your homework in 8-7 because you also have the midpoint rule. So let's just say you guys get to do something like 5-2, maybe 17 odd. I think I just added one more. So you guys can try some of these homework questions, okay? Let's make sure you guys do stuff like that. So this morning we finally got to Simpson's rule, and midpoint rule is nice too. So to let you guys know on a test, definitely, which one do you think on a test? Let's see if you guys are awake, right? Which one would I most likely, almost certain to ask? Of all 4 of these techniques, which one should I ask? Do you guys know on a test? I know there's a delay here. So if you said on your homework, which ones do you think are the most important that you could possibly see one day? If I had Flaming Hots, I'd give it to the first person who knows the answer. Anybody? What do you guys think? Which will be on a test? AL? No. AL? Yes. Sam? Yes. Okay, you guys are awake. Yeah, don't do. We didn't cover the trapezoid rule, so don't worry about that one. Okay, I would say if you guys really wanted to study some of these things, definitely look at the midpoint rule, look at Simpson's rule on your test. Final blah blah blah, all those things. Definitely Simpson's rule. I think is it even the name? No, it's not even the name of the section, but it's the name I think of when I see this numerical approximation. So Simpson's rule, ladies and gentlemen, and work on some midpoint rule. Who knows? I might put that there too. So definitely do the Simpson's rule. But that's your homework. So I'm going to let you guys go. I have another class coming, and I wish you guys well today. Work on some of these questions here, and we're going to start tomorrow on arc length. So I'll see you guys tomorrow. If you have any questions or issues, come to my office hours today, and we can talk about that and go over it. So I wish you guys well today. Have a great day and take care.